Hello, what's up, everybody? Long time no see. As a quick explanation, I guess, of where I've been basically writing a ton of Rust code at work every day. So that's kind of diminished my motivation to come home and do the same on the weekends. So let me just hop in here and let's see how much Rust I've written. About 14,000 lines. So I've written a lot of Rust code since I last made a video, and the other exciting news I have is that it seems, hopefully, that the main research code I've been working on in that time has produced the data we need for a paper. So I'm back in paper writing mode instead of code writing mode. So that's left me with some code writing energy for the weekend. So this is, as I'm sure you can see from the video title, this is another qcrab video. The first thing I want to do is do a little bit of refactoring. I haven't really looked through the code that much. I did open it up, as you can see here. So I haven't really looked at it since last time I did a video. So I want to do a little bit of refactoring, I assume, because I think this is basically the first Rust code I wrote. And then I would like to finish out this first Crawford project today. So those are the goals for the video, and yeah, so that's about it. So I looked through the code enough to see that I think we made it through step 6. So all that's really left is to compute the principal moments of inertia, compute the rotational constants from that, and then I'll go ahead and finish out the test cases. The very first thing I want to do is to just format the buffer. Let me do it somewhere that you can actually see it have an effect. So I think the default Rust font max line width is 100, and I prefer it to be 80. So I have a global Rust font config now. So just hitting my key binding for that handled that. So I'll go ahead and commit that as its own change. So Rust font to 80 columns. Oh, and the other thing I wanted to do that I've started doing in my Rust and my old Go projects is to add a commit hook that runs the formatting. So I started noticing that sometimes I was forgetting to format my buffers before committing the code. So one thing I like to do now is just find, I'm going to do it like this, .get hooks. I've been adding a pre-commit hook to, let's just copy this to pre-commit. That basically just calls cargo things. So there we go. Now, every time I go to make a commit, it'll run that hook. And the way this usually works is that I'll make some change, I'll commit it. When I hit Control-C and Magit to finalize the commit message I typed, I'll see some additional changes here, and then I'll just hit CE to extend my previous commit. So it's not perfect, it doesn't like catch it before the commit or anything, but at least it catches it eventually. So the very first thing to do, I guess, is to make sure I've also started using a makefile again. So the main thing is just cargo test. But I also typically like to do something like this. And I usually go ahead and add no capture, because I think by default cargo hides all the output from you. And I like to know in the cases that there's output I want to see, and also in the cases where there's output I don't want to see. So if I've left some kind of debugging prints inside of the code, I want that to come out in the test. So I'll go ahead and add test flags no capture, and later on if I run into some kind of concurrency issue between the tests, then I can add like test threads equals 1 or something too. But for now, no capture should be good enough. And with all of that done, let's go ahead and run make test. Just make sure that the tests I wrote before do pass. Excellent. So what I've just done there is to turn off that compile notification you have, or that you may have seen in the top right of my screen. I have that set up because in a lot of my projects I have like very long compilation processes. Not really that long, but you know, 1 minute, 5 minutes feels very long sometimes. So I'll go do something else and I'll see the notification and come back. Okay, so what do we need to do? The first thing I want to do actually, I think, is to add a procs as a development dependency, because that will let me actually write some macros that compare the equality of molecules to like an explicit epsilon value. So as you see here, when I originally wrote this, I think I may have tried a procs even, but I couldn't figure it out back then somehow. So now I know how the crate works, and so I can actually, what I would impl here is actually impl abs. What are they? I think they call it abs diff eq for molecule. And I also realized that I can add things as development dependencies instead of, although I needed to check how that works. Dev dependency rest. Is that right? I kind of thought you just put dev. Okay, nope, that's right. Okay, so what I will do, I'm going to add assert cpf to find my project file, cargo toml. Oh, it is still in here actually. So I will change that to a dev dependency. Dependencies. Okay, and then the other bit of refactoring I want to do, first of all, I'm going to go ahead and move my tests to their own file. I'm going to call these mole tests. Okay. Mole tests. Perfect. Now I'll put this up at the top. Let's make sure that our tests run. Perfect, they don't run. Okay, so I need to go ahead and import a bunch of stuff. One thing I do miss about Go is that it would just handle all of these imports with Go imports, which is like a replacement for Go funct. But doing it like this is okay. It does work at least. Okay, yeah, this is going to change a lot, I think, with the refactoring. Okay, so let's see. Hopefully it passes now. Excellent. Okay, so now that we have that, let me go and move the documentation to the right page. I realized that forwarding style. There we go. Okay, so we move that to a test module. Perfect. The other thing I want to do is actually move oh no. Each on I think what I want to do is I'm going to make this I'm going to rename this to load self. Let's spread these out. What I'm thinking about right now, do I want this to be new or default? I might make this the default implementation. Actually, I think we can just derive default, right? Debug default. Because both, yeah, so I'll just get rid of this actually. Okay, great. No region. CPR. I want to replace region with molecule load. It's going to prompt me. What a nightmare. Alright, did that work? Okay, great. And here, change this to default. Okay, great. The other thing I was debating doing is moving the molecule to its own module, which I think is what I'd like to do. But the fact is, the only code I have in librs right now refers to molecule. So in that case, it doesn't seem quite as pressing. Well, I guess there is like bond. Partial Q. I don't think. Let's see. I think this stuff must only be tested. Oops. Oh no, I shouldn't have done that. I just want to see if the partial EQ... Basically I want to see if a prox needs to be a dev dependency or a real dependency. I'm assuming it only needs to be a dev dependency because I think... sorry, the phone's making noise. I don't think I actually test this equality in the actual code. So, but I like to take a look real quick. qcrab. Ooh, failed. Failed to open geom file. Ah, yes. Dev shot, excellent. Okay, so I'm pretty sure that this stuff can actually go in the test module even. In the tests. Yeah, I guess that's actually the better test for it. What? Okay, that's fine. Okay, what doesn't I like about this? First implementation here. Oh. Yeah, a little slow to update. Okay, now if I were to delete this... Oh, that's my calculator. Yeah, must implement partial EQ because we assert EQ. Okay, so what I actually want to implement is approx abs diff EQ. Do that, and then missing members. So I will take what I have for EQ and put it in here. And I'll make the default epsilon. what I put in here before. Let me take this stuff out. Oh, no, that's not right. Perfect. Okay. Why is it mad? That doesn't sound right. Can't compare molecule. Perfect. Okay. What's the problem now? Missing match arm. What? Oh, right. Pass, pass, pass. Excellent. Test center mass. This returns a new molecule, right? Ooh. Vector 3. Oh, okay. How many decibels? Oh, okay, perfect. 2? Try to tighten up the bounds. Oh, okay, so 1 is a little too tight. 2 works. Okay. Vertical angles. Those are exactly the same. Perfect. Ah, wait, is that because of Tor's? These should be partially Q's, or have stiffy Q's as well. Oh, the pain. Okay. What a mess. Well, that's neat. So this means that the molecule is actually exactly equal. That's good. What if I just delete this in the bonds field? Yeah, okay. You can't derive abs if you keep my personal browser tabs. I don't think you can do this. Yeah, that's what I thought. Okay, abs if you Q, not for molecule, for bonds. let's see, I'm just going to borrow this code. Ah, yes. Bond. No, what now? Bond clone is not satisfied. Okay. Well, I see why I didn't do this originally. And I know this because of the comma at the end. Expected struct dynamic found const. Yeah, one of them's constant, one of them's not, so I'll make this d vector just to make the types the same. Okay, great. This, the reason I prefer doing the abs diff EQ stuff, instead of just having these random cutoff values or epsilon values embedded in the partial EQ implementations, is because then at least you can specify exactly what you're looking for. So, like in the tests, I don't have to be like, or if I know that the constraints are actually tighter, then I can do that. I don't always have to defer to this like 1 E-6 value. So let's make this ab stiff EQ again. Implement the missing members. Put this down here. 1 E-6. Okay, try this again. Can't compare angle with angle. So now okay, go back to angle. The other thing I should probably do is make something partial cube. Okay, and let me go ahead and do this for the torsion. Cube. Oh, I deleted it too soon. Hold on. What? Okay. Do we pass? Oh, of course not, because so the molecules are the same. That's an actually really nice thing that I've found with Rust, is that when you parse in floats, you always can say that they're exactly equal. Like I pasted these values in from the file that's being read when I call molecule load, and the values are the same. So you see, I didn't have to do a prox here. And also this nonsense I had to do here was because abs_diffq is not implemented for vectors or even slices, I think. So the easiest thing I found to do is just convert them to in algebra's d vectors, and then you can just slot those straight into the abs_diffq macro. Alright, so bond angles failed. abs_diffq. Same thing again, yep. We'll do it again. Okay, is it mad that it doesn't do clone? Okay, perfect. And we'll put clone on this as well. What? This will be the same. Holy moly, that's a lot of stuff. And I'll take that here as well. Okay. What all did we do? We did a lot of stuff. Okay, move. Test to separate module. Use the props for quality tests. Great, and I'll just throw those in as well. Okay, so let's see what we have left over here. I kind of think, I vaguely remember not making these methods for some reason, but I think it should be a method, actually. Load, dist, angle, center mass, translate, unit. I kind of think that in algebra actually has something like that. In algebra, it's like dist or something. Base unit. Or hypotenuse. Let's see. Where's dots? Oh yeah, the other thing I meant to, I should have mentioned this at the beginning of the video. I wanted to switch to live streaming for the format of these videos, but I did a speed test this morning, and my upload speed was like 0.08 megabits per second. My download speed seems fine, so most of the stuff I do on the internet is like unaffected, but my upload speed is just atrocious. So I can't actually do live streams. If I get better internet in the future, I may switch to that, because that I would prefer to do that so I can actually interact with people while I'm doing this, rather than it all being later. But yeah, right now I can't do live streams, so hopefully you still get something out of watching these videos in the static form. It's not really hypotenuse, is it? I'm looking for E over V dot magnitude. Alright, well anyway, that's not a big deal. So I think that's most of the refactoring. I haven't even actually looked at any of the code. Alright, let's do a quick scan of the code to see if I want to refactor anything. I wrote anything badly. Okay, so something that I have learned is that you can just do flatten here, and then you can do this. I think, can you just skip one? You probably have to unwrap that, don't you? What's the problem? Expected comma. What? Why did we expect the comma? Okay, there we go. So, yeah, I learned about this in the book. What's it called? Programming Rust. I finally finished reading that. Great book. Highly recommend it if you're interested in learning Rust. I thought it had... I thought it took like a really gradual introduction. So, maybe it was because I'd already written a little bit of Rust and I had been reading the Rust book online. But I thought it was a really smooth read. Yeah, a really enjoyable book. Well written, great examples. So yeah, I highly recommend it. Anyway, but I saw this in there where you can just flatten, because there's a lot of discussion of iterators in the book, and this is one of the cool tricks in iterators. If you flatten an iterator, it will just like unpack the options or the results or whatever. It'll just like discard the error or none values, I think. So this is a really clean way, in my opinion, to get rid of the potential errors from reading a file line by line. Let's see. I also learned that you can do like, that you can just do that. So you don't have to actually figure it out every time. Let's see, parse, expect. This all looks okay. But, I mean, if you have figured out the types, it's like pointless to make that change. Okay, so that looks good. This is nice little refactor. The distance between two things. Perfect. Okay. Bond angles. Yes, this looks very familiar. Center of mass. Okay. Wait, did I just... What is this? Zip, zip, zip. Okay. Zip. This all looks fine. Stars use view size. So this is the total mass. Okay, great. This all looks good. What to do about these? So these are kind of all... Something I'm thinking is making these enums, right? Because to some extent they're all variants of like a geometrical parameter, but I'm not sure that that really fits cleanly, which I think is why I didn't do it before. I just hate having them all separated out like this. But I guess it's fine. Unit vector, this like doesn't really belong here in the middle of this. But anyway, maybe well, so this stuff at least, I'm going to move into the module, or into the molecule. Okay, the other thing, let's go ahead and make another module. Mod molecule. So what I was just making that face about is it probably be nicer to have some intermediate struct, which is what I've done in some of my other programs, where you have like a struct atom that contains a Z I32. Why is it an I32? Unclear. It should just be a U size. Cores. Which is a vector 3 of HC4, like this. And then a molecule just becomes a vec of atom. Do I like that better? And then you can even change Z to atomic charge, right? I don't really feel like doing that right now, but I think that's preferable because then you don't have to worry about these vectors being different sizes. I mean, obviously, if you program correctly, they will not be different sizes, but combining the parts of an atom inside of a molecule into a single entity, I think, makes more sense from that perspective. And then some of the things that are methods on molecule can probably be methods on atoms. Like, we could have a method to look up the mass of an atom. This is what I've done, again, in some of my other things. And I did think about actually trying to use some of my other libraries that I've written in qcrab, but I think at least for now, I'm going to keep qcrab as a standalone project, partly for the videos and partly just for fun, I guess. Actually, basically entirely for the videos. If I were doing this on my own, I would just import my own molecule from the other crate I wrote. But let's go ahead and do what I was just saying. I think it's been a while since I ran the test. Let me just run the test again. Yeah, perfect. Unresolved imports. Okay, great. Yes. Let's go back to lib. And I'm going to pub use molecule. I always forget how to make this work. Pub use. Oh, that's right. You have to have a pub mod. What's the problem now? This way? I think it's this way. Pub use. I always forget how to do this. Pub use. Pub use. Is this what you have to do? Okay, good. Hoop angles, torsional angles, bond angles, and bond lengths. Okay. Then I'll move the unit vector over here. Helper function. Okay. Then we just have all of our different coordinate types in here. Okay, so P table actually goes over here. Oh yes, take all this out. Let's see, are we down to this stuff? Okay. Cannot find function bond lengths. Okay. So now we can go back over here. Load. Dist. Bond lengths. No. Okay. Gonna find mole. Okay. So we're gonna fix this later. Okay, now what's the problem? Get rid of these warnings. This is going to be used shortly. That's okay. What? Isn't this used in here? It's used right there. I see. So many warnings. Okay. Alright, here we go. Now we can start taking this stuff. Okay. And this is why I can put this back into the molecule. So one thing I'm not really sure about is whether I prefer putting these at the bottom or at the top. Why doesn't it like this? Oh! Alright, I'll make it a real dependency again. Ah, okay. And so this is why I changed it to direct default, because now I can do this. Z's, back, y2, and towards, back, 3, 64. Oh, whoops. Alright, there we go. Okay. Move molecule to okay, now let's do the other change I was talking about. Yeah, it can be U size. Chords are vector. Alright, hold on. Yeah. The other thing I do like to do is to define a type alias. So I'll say type vec3 equals vector3 of f64. That way I don't have to keep typing in a vector3 everywhere. Okay, so I'm going to call this vec3. Use import create vec3, perfect. And then we'll change this to a unit. Well, not unit, a tuple struct, is that right? Where is a vec of add. And this is just chord, like that. It's going to get mad because I don't have all of this. Shot. Perfect. Okay. Actually, I do prefer this, I think, where you do it like this. So, then I can say, oh, whoops. Perfect. Okay, is there a reason I didn't do this before? Let's find out. Mul.z.push. I don't think so. So I think what I'm going to do now, mul.atoms.push an atom of atomic number is going to be this. Okay. Do this. Okay. Uh-oh. Okay, yes, that's right. Okay. Is that what it's called? Yeah, okay, that's just a mistake. Whoops. Unknown. Okay. No field Z's on type molecule. Yeah, so what I can do now, let's do this. Number, word, or atom self.atoms. Much better. Type U size cannot be dereferenced here. Perfect. Can you rust destructure and that would be pretty sweet. I don't know. I know you can do it for tuples, obviously, because that's how enumerate works. But I don't know. Can I destructure a? Can I destructure this here? Oh, that is so cool! Oh my god, okay, I didn't know you could do that. Wow, that is cool. Oxford comma, can't forget. Gotta add some documentation, you know? Alright, how's it looking? Unused import. There's really only one length of a molecule, so the other thing I could do is just implement len as a method on molecule, right? Like there's a pretty obvious way to compute the length of a molecule. No field. So now the actual important derivation here is this. We're going to implement it on atom. That's not important anymore. Self.cord. No. The question now is self.cord. What is that? Oh, this is the reason. Okay, yes. From Vex. I see. Yeah, okay. So this one takes Z's that U size and a vec 3's. That's why I screwed over earlier. Okay, Z chord and zip Z's. Alright, this returned a self. Probably just do this with an iterator, like collect them at the end, but this is probably good enough. Okay. Cannot move out of, okay. And now I have to do this. Not sure why that didn't pop up before. Go to a new X. Whoops. This is why I really wish you could derive it. Okay. Null test. Simple crux. As molecule. missing members, 64, 40 minus 7, 4 you can write this as an iterator too. Self dot other dot self. Jeez. And so let's zip again. All. Oh, wait, hold on. E dot abs diff E. Where do I have to call? Oh, perfect. Okay, I guess this is nicer than the for loop option, right? Because it reads pretty cleanly. Zip self atoms, other atoms together, and assert that they all are equal. Oh, we did it. That was a more painful refactoring than I expected. Okay. Atom inside molecule. Make molecule a vector atom. Okay, so that should be all of the refactoring I wanted to get done. So now let's actually click the button on my mouse. Now let's actually implement this last bit here. Principal moments of inertia. So I don't want. Is that right? We got the center mass. Alright, let's do some PDD here. Mole tests. Test translate. Let's see. Does it give us? So we're not going to look at the solution code. Does it give us the output? Maybe. Moment of inertia tensors right here. So test MOI. Let's go back. We need a molecule. We need to do this translation. Once we've translated it to the center of mass, we need to compute the moment of inertia. Moment of inertia. Let mole equal this. And then we're going to call. No, this will be got. Let 1 equal. What are these? It looks like 12, 3, 6, 7, 8, 9, 10, 11. No way. Okay, 12. So we should be able to agree that far. And what we want is this. Why are you mad? Oh, right. Is that how you do it? Why is it mad? Well, it certainly seemed to work. Alright, so I'll come over here. Vacuum molecule, ample molecule, hub, FN, MOI, moment of inertia. And mat 3, which I'll define in a moment. To do. Oh. Okay, great. So the reason I've skipped formatting this, as you probably saw before, is it wrapped them all into lines. But I'd really like it to look more like a matrix here. So I'll just tell Rustpump to leave it alone. If I run the test now, mat 3 not found in scope. Matrix 3 of F64s. Import this. And now it should panic it unimplemented. Perfect. Okay. So let's hop back over here and see what it's asking us to do. So it looks like we're going to be looping over. I don't know if this is big enough for the video. But basically we're going to be looping over the atoms again. So all I'm going to do I actually need I is the question. I don't think so. So, alright, we need a new mat 3, I think. Mat 3 zeros. Oh. Okay. So, yes. Okay. Where is it that I do p-table? Where do I refer to this? Okay. Well, this is really cool, but I'm taking it out. For atom and self.atoms, let mi equal atom.mass. And then this is just the atom.float. So let's add an impl block of fn mass. So it's going to return, it returns an F64. So it's just going to take p-table of self.atomic. Great. Pass. Doesn't pass because of this. Perfect. 0 doesn't equal all of that stuff. Who knew? Alright. MOI. Okay, so we loop over. Off diagonal, add a negative sign. MI. Alright, so let MI equal atom.mass. Perfect. I'll just do it like this. Concept. That way I can actually access it like this. And I can even change the name of this stuff. Fine. So I can say I of x plus equals mi times Adam dot. You can actually do this. Y dot how I2 plus Adam dot Z dot Howie Oh, does it not have this? Beautiful. mi times xi plus zi and zz is xi plus yi squared. Okay? Alright. Fine. It wants some uppercase. See, I wanted those lowercase and this uppercase. I know you can ignore like snake case names, but I don't know. It's not a big enough deal for me to do that. Okay. I'm running out of time, so hopefully I can finish this soon. Why does this say add a negative sign? I'm sure we'll find out soon. Diagonal. Off diagonal. Okay, let's just take all of this. XY. XZ. YZ. Okay, XI. Adam.core.x times Adam.core.y. Core.x times Adam.core.z. And this is YZ. Let's see if it works. Okay, to the pass. Looks pretty good, but I think so. The diagonals look great. It looks like I need to add a minus sign, in which case I should probably do minus equals. And it also looks like I need to mirror them across the diagonal, which makes sense to me. Minus 52, 54. Okay. In true Fortran fashion, let me go ahead and do it like this. Actually, yx equals xy yz xz and zx. Oh, whoops. Wow, I messed that up. Zy is yz. Okay. Why is it mad about this? That is a right bracket. Yep, that looks the same. I think we just need to modify our epsilon. Let's try 11. Ooh, 10. Alright, let me look at this again. The other really nice thing about 12 gonna be enough. Let's do 0.10. About in algebra, I think I was like kind of talking trash about in algebra when I first used it, and I will see that it is a bit different from the Go stuff I've used, but it's very nice, actually. Oh, that's pretty different. It's very nice. In algebra is very nice. So if I did say anything bad about it, I take it back. I really enjoy working with it. Don't mind at all. What's going on here? github.com/mtbre/kim761. Oh, I'm not signed in. Okay. Yeah, if I could live stream, I would probably stream some chess as well, but unfortunately not. I'm just checking to make sure if I did something wrong, or if, okay. 1 times 10 to the -6. Obviously I can keep relaxing epsilon until I find something that works, but what I was hoping to determine is if I should expect to have to decrease epsilon, or increase epsilon to this extent. Okay, so again, that's why I turned on the no capture thing, so I can actually see this stuff coming out. Test. Let's try, since it runs so fast, we'll play with it a little bit and see if we can get, oh, I went the wrong way. Let's see if we can get tighter criteria here. So. Alright, great. Write and test moment of inertia. And this is the formatting thing I mentioned, so I'll just stage it and then extend the previous commit. And let's take a look at the last thing we need to do. I've got to do something at 3 o'clock, so hopefully I can finish before then. Rotational constants. Ah, yes. So I think all we do, diagonalize this, take the eigen, oh, is that right? Oh, did I skip a step? Oh, diagonalization. Ah. Okay, I forgot that step. Diagonalize the inertia tensor. Okay, sure. I forgot to do that. Oh, the part I was thinking about. So the other useful thing that you can do with the moment of inertia tensor is that you can align a molecule with the Cartesian axes. This is, okay, yes, because I do this in my symmetry package I wrote a little while ago. I forgot that the Crawford Projects they compute the moment of inertia tensor, and then you diagonalize it to obtain these. So when you do this, you're going to obtain the principal moments of inertia as the eigenvalues. But what you can do with the eigenvectors is you can just multiply that onto the coordinates of your molecule, and that will rotate it so that the principal moments of inertia, or that the principal axes align with the Cartesian axes. So I use that to normalize molecular structures I read into my program. So I read it in, I compute the center of mass, translate to the center of mass, and then you can use the moment of inertia tensor, like I keep saying, to rotate it to some ideal alignment. And then the other thing I can do is that just aligns it with some set of the Cartesian axes. So then you can look at each of those axes and orient the molecule how you want. So for example, if you want one of the axes, depending on the symmetry of the molecule, if you want it to be on one of the axes, you can just then turn your coordinate system, or basically reorder the columns of your coordinate matrix to reflect that. So that's how I transform atoms into more consistent format for what I've been working on. But yes, so now that we have the moment of inertia, do we even care to... I don't even really care to actually get the moments of inertia themselves. I pretty much... I don't really care about doing this part either. Alright, let me diagonalize this. I'm not really sure where to do that. Let's just do it inside of a test. Test ruts. So, I'll just grab this. I just want to show how you do this. I'm not sure exactly where it's going to go in the code right now. And I do have to go soon. So, I will just do it here. Okay, so this is my moment of inertia. Once I have that, the way you do this within algebra is you're going to do NA, ln alg. Because it's a symmetric matrix, we know that because of the goofy copying across the diagonal we did. We can go ahead and do a Cholesky decomposition on the matrix. So the first step is to do the Cholesky decomposition. I'm going to match on this. What? Come on. What? Oh, duh. God, why do I keep forgetting that today? Okay, so now I can match on that. So, fill match arms. None. Panic. Cholesky decomposition failed. So great. So we get that. I guess we could just unwrap, since that's basically what we're doing. The other thing you can do here, note, if positive semi-definiteness might break down, fall back to LU decomposition. So if I'm remembering my Wikipedia correctly, Cholesky decomposition, Cholesky is a decomposition of a Hermitian positive definite matrix. When it's applicable, it's roughly twice as efficient as the LU decomposition. So, yeah, so positive semi-definite, I think I've seen abbreviated as PSD, so that's why I did it there. If that breaks down, like Wikipedia says, you can fall back on the LU decomposition. So that's just ln alg LU, nu on mol, or moi in this case. But I'm not going to do that here because this should definitely always be symmetric. So this is the new code. And then we can just factorize, or what can we get here? Did I mess this up? Is this not what you want to do? I'm going to have to look at it in algebra. Oh. Can I just call that on any matrix? Ah, okay, sure. Well, sorry, I was thinking about something else. Let evals equal dot expect field to diagonalize And let's just debug those for now. What is going on? Alright, let's see if these look right. Alright, well, that was a bit of a tangent, but hopefully it will help if you ever need to invert a matrix or something. Which we'll probably need to do in the future here. So let's check our inertia. 31, 178, 199. Okay. And what does this come out as? It comes out as a matrix. I don't think it's returned yet. Can I not even call it on that? What? I think I can do this. Oh god, this is annoying. Swear to God. So seeing this does not need to be mutable. Okay. Let's try to figure this out. Cannot borrow evals is mutable. This is I'm doing something stupid here, I'm sure. I think it's something to do with this being a slice and not a vector. Yeah, okay, there we go. So let's see this now. And I think that's going to sort them in the wrong order. So just replace these. Okay. Yeah, and that's why I usually add this so that it doesn't get mixed up. So now, the first one is going to be IA. The second one, okay, and these are in AMU or square. Okay. So, just to finish this off, we need to apply these formulas. Oh god, then I have to go get their physical constants. Alright, that's probably going to be it for today then. Hopefully you guys enjoyed the video. Hopefully I got to show off some of my... Probably not, I don't think I have any new Rust tooling that I got to show off today, but maybe I got to show off some of my Rust expertise. And I'm sure people will let me know in the comments if I destroyed everything. But anyway, as always, thanks for watching, and I'll see you next time when I will hopefully finish off the rotational constants, just doing a little math. The reason I'm delaying it right now is because I kind of want to think about where to put this code. So, do we ever need the moment of inertia tensor itself, or should I just have, like, do I want to have an MOI method and also have a principal moments of inertia? Do I also want to have a moments of inertia method, and then do I also want to have a rotational constants method, is basically what I'm wondering. For the sake of reproducing their output, as you probably saw, you would probably want it like that, but I'm just wondering if these are even like applicable in the future. So anyway, I'm running out of time to test those robustly and also to do that. So I guess there will be another video where I'll finish off this part, add the test like I said, and then eventually move on to project number 2 where we get to use the vibrational frequencies. But anyway, thank you for watching, and I'll see you all next time.